Welcome everybody to Lecture 5, Databases and Information Systems, the course which can also be taken as information retrieval this semester. Particularly nice weather today, which is maybe the reason for the slightly fewer than usual people in the room. But nevertheless, let's carry on. We will talk about your experiences with exercise sheet 4, which was about coding a simple database management system, asking a few queries on it. And today we will continue with all this. I'm not going into the details here. The exercise sheet, I've chosen the heading Next Level SQL. So you will, and we will talk about it later in the lecture. So it's one more lecture about databases and SQL, but next level. So if you sit down, please lift the chair and don't drag it over the ground. Thank you. So here are some quotes from your experiences with the last exercise sheet. The lecture and the exercise were very well explained. I really like that we discussed efficiency. Many of you said that, so I think in a typical database lecture course, you don't hear much about efficiency, but I think it's just central. It doesn't make much sense to talk about databases without efficiency. Just think about Cartesian product. I mean, this starts to become efficient already for a very small query. The efficiency aspects of different approaches is even exciting. Thanks for this great exercise. The result table is motivating, so you could code something, try out your query, do the theory, then also see what the real running times were. And some people found that their first attempts were not so good, but then they saw what others achieved, and so. And by the way, if you don't do the exercises, absolutely, you have to do the exercises to understand this stuff. The sheet was the best one so far. I liked it. Interesting sheet, quite easy to accomplish, but learned a lot. Okay, I don't think it was easy for everyone, but would have been cool to come up with a SQL query myself, yes. For this exercise sheet, we have more complicated questions and queries, and one task will be to come up with a SQL query yourself, and it will not be easy. Yeah, and a lot of things went wrong in the last lecture, basically everything. Let's see what happens today. So maybe the bad weather compensates for everything. Okay, so let's continue from the last lecture, and I've included a few slides from the last lecture, just so to get into the mood again, the hash join. And this was so you already worked with the hash join in the exercise sheet. This was the formal definition. I will not repeat it, but let's look at the example. So please pay attention, understand the example again, and then we will move on to the merge join, for which we didn't have time in the last lecture. Let's understand these example tables here. They are sort of very small so that we can put them on a slide. So we have here, okay, the schema is not here, but you see the schema here. We have two tables, professors and the courses they give. So we have Brox, Hutter, Bast, Burgard here. And here we have students participating in courses, just very few because the tables are small. And now we want to join the tables. And we have seen, okay, the example. Maybe let me show that again, because that I think was, maybe I should have included that on the slides of just to get into this again. This should have been towards the end of the last lecture. Yeah, this was the correct, here we have the schema and the table, right? That's how you do it. So it's important also for what comes in 10 minutes or so. There are some professors here which don't have students here. So for example, Brox, there's a course here, there's no course here, so it will not be in the result. And there are some professors here where we have some courses with multiple professors, right? So for example, this here was, so understand this again. Here we have a course called V0240, that's an ID, and it has 3 students and 2 professors, which means we have 6 results in the join. So let me say that once more. So this cross product, Cartesian product thing can also happen on a micro level, and does happen on a micro level when you do joins. A course with 2 2 lecturers, 2 professors, 3 students, you get all combinations in the result. So that's why you have these 6 rows. Then you have one course here, 1304, with 1 student, that gives another row, so 7 rows. And this course here has no students in this table, so no more rows. So, and we talked about, and you implemented this, how you do this with a hash map. Maybe let's also quickly recap that. There's enough time for that, I think. It's important that you now, only for the purposes of the computation, to give the row indices. I mean, it's not in the abstract model, this is just a set, but when you work with it algorithmically, then temporarily you have to give them row indices. So here we have 1, 2, 3, 4, here we have 1, 2, 3, 4, 5, 6. And now we compute this hash map for this one table. We could also do it for the other table. We have 3 different courses, and the keys are the courses because that's the column on which we want to join. So 3 different courses, 1 course with 2 professors, and here we have a map which rows, not which other column, but these are the row indices where we have this thing. So course 2042, we have rows 2 and 4. And now with that hash map, and that's how a hash join works, we can now go over this table. Let's do that again. We do course after course. We can go in any order. V1304, is it in the hash map? Yes, it's there with with this row 3, and so I'm taking this and combining it with row 3, and that's what I write here. Then I take the next one, V0240, is it in my hash map? Yes, with 2 rows, 2, 4. So I take this row and combine it with this row, which is why I have these 2 rows here. That was the hash join. Is there any, you implemented it, at least those who did the exercise sheet. Any question about this before we move on to the new stuff, which is the merge join, which is also not much more complicated. Okay, so this was just warming up so far. And we already talked about this. Maybe let's also recap this, because the merge join has something similar. What's the time for this? I mean, I have to build a hash map over this table. So I go over the table once and I insert into the hash map. So if I have 20 rows here, I have 20 inserts. And then I go over this one and do lookups in the hash table. So I have as many inserts as I have rows here, as many lookups as I have rows here. And then I have to create this table, which is a certain number of rows and columns. And that's why I get this many. So this is like the number of inserts, number of rows in the first table, number of lookups, number of rows in the second table. And this is just the size of the result, which can be large due to this cross-product effect. And also understand, let me also say this again. So we are doing join operations because it's more efficient than first doing Cartesian product and then filtering. This is really important. This cross-product effect also occurs here on a micro level, but if it would so happen that all values here are the same and all values here are the same, even a hash join or a merge join, a join, would compute the full Cartesian product. And this can also happen on a, just assume this is a big table and half of the values are the same here and here. This would also give you a very big table, which is why it's important that I have this here in the running time. So if my table is large, this will be an expensive operation. Now let's do the merge join. And this is the abstract description, but let's first do it by an example. And now comes a very interesting connection to the first and second lecture, because now we will do something which very much looks like an inverted index, which is an inverted index. So for each list, I first compute, so for x, I'm not sure how much space I need, so this is my table x here, and this is my table y here. One cannot see a blue y written on blue background. So let's start with X. Now I do the same thing. Not quite the same thing. I sort these values in the join column. And that's also what's written on the previous slide. We have the values in the join columns in sorted order. But I have to remember from which row it comes. So let's do that, best understood by an example. So I'm sorting these here, and I sort them lexicographically. Let's see whether it works. So that should be V720, and this comes from 1. And maybe I do the 1 in another color, so that it's clear that these are the row indices. So this here are I temporarily give them row indices again. 4, 5, 6. Okay, now I need to do a bit of pen switching. And now I have to do, okay, what's the next one? It's V1304, comma, something, comma, okay. I think I have to write it here on a new line. 2042, comma, and then I have another one, 2042, comma. Okay, and this is, so I sort by the values and I remember from which row they come. That's a typical thing to do in sorting. 2, 4. Yeah, it's now the values of the join column. Now I have to do the same thing for the other table, and let's do that. So yeah, it has to go over multiple lines. So what's the first one? S comes before V, right? 13. And let me leave the space for the row index open. What's next? 1304, right? 1304, comma, and what's next? Next is, and now come 4 times V2040, comma something, V2040, comma something. Yeah, and it's a multi-line list. And this should remind you of an inverted index. So, and this here comes from row 6. This one comes from row 1. So it's really just sorting the values, and this I just do it in this order. 2, 3, 4, 5. Any questions about this? Yes, please.
There are not 4 of these 2040, there's not 2016.
So I did a mistake. Where did I do a mistake? Which element in which list?
The last element in the Y list, the line 4 in the Y table, has another course number.
Oh, that was wrong. Yeah, exactly. Thank you for paying attention. Yeah, it's not a mistake here. It's actually, so yeah, it's more interesting then. That's good. 2, no, that was actually fine. Thank you very much. Could just claim I did it on purpose, so to check whether you pay attention, but I didn't do it on purpose. It was, so, that's correct now? Yes?
There are 2 4s as row indices in the Y list.
2, 3, 4, that's a 6, 5 now, right? Huh. I'm sorry. Okay, now let's 2, 3, 5. Let's just check this here. Yeah, this is 2, 3, and 5. And this should very much, and this V here is a bit malformed because I thought about a Y. You shouldn't think about different things when you, and this should very much remind you of an inverted index, right? Here I have it in order of, this is an inverted index. Here I have the rows in order of some temporary row indices, and now I take take it just in different ordering. So if I would sort this by row index, I would just get the rows in this order, and now I sort it by the values in this column, so I'm inverting. Yeah, it's effectively an inverted index. And now, for the result, now I can do the same thing, and that was on the previous slide, and that's the important message here. I can use the zipper algorithm. This is now I have two sorted lists of integers, and whenever you have that, you can do this linear time intersect. And now let's, and maybe, I mean, you don't have to compute what I now write, but maybe just for the sake of, so the result is, so how do I do this? I start here, and I start here, and now I compare these two values here. Are they the same? No, they are not the same. And then I advance in the list with the smaller one, right? S is smaller than V, so I advance here. Are these the same? No, they are not the same. So now I advance here. And now one important detail, so now they are equal, so I will certainly write, and let me do that, this result in the, and now it's a little variation. The question is, what do I write in the result? I mean, this is, I don't really have to materialize this, but I'm doing it. So maybe I just 3, 1. So I have this now. So this means I have this in table in row 3 from this result, and in row 1 from this table here, and so on. And now, okay, we don't see it here. I have to check whether this occurs multiple times here or there. It's not the case, but we will soon see it to be the case. So that's one important difference here. So now I'm continuing in both lists, because I've already processed this one. And now I'm here, so that's another match. So I will get now, and let me just write V 2040. And now that's a little variation of the inside the zipper algorithm. When I have and this is actually something we could have talked about in the first lecture. What do you do in intersection if you have several times the same value here and here? You somehow have to define what you do. I have this value twice here and 3 times here. And a very common thing to do, and the right thing to do for a join, is to write all combinations in the result. And that's what we will do. So inside the zipper algorithm, you now need a little loop. You first, that's when you would implement this. You don't have to implement it for the sheet, maybe for the exam. You now have to check, okay, how long is my sequence of V240s here? It's 2. And maybe I symbolize this by having a dotted line here. And this is something you can easily check. Let me just check how much of the same ones I have. And now, and understand that this is efficient. Now I have to output all combinations. And I mean, I have to produce them, right? It's 6 combinations. I have to write 6 rows to the result. So it's also efficient to just do all combinations here. I can't do it any better because I have to write 6 rows to the result. So let's just write them here. And 2040, 1, 2, 3, 4. And this result table which I'm writing here, you don't really have to materialize it. You can directly write the table on the left, but I'm just doing it here to clarify what I'm doing. That's a bit, because I don't want to switch the pen so often. And now so now I have all combinations here. So it's 2 from the first table and 2 from the second one. It's 2, 3. It's 2, 5, and now the same with the 4 from the first table. 4, 4, 4, 2, 3, 5. So, and this is, let me just also clarify this. This is from X. Wow. Where does this come from? Outer space? toilet, cooking, inside the body. So, and now I have the result in this abstract form, right? What does it say? Let's just look at, for example, now let's maybe look at 2 rows here. For example, this one. And let's write this here to this first row. And what it just says, let's just make this, it just says, okay, this value here, 1304, it's an equi-join, so I will have that in both tables here, V13, and the result is exactly the same as for the hash join, of course, just a different algorithm. And now I need the, from table X, the third row, so it's Bast here, and the first row here, so it will be 7, 3, 8, 3, 4, 3, 6. And whenever you spot a mistake, please tell me. So there will be 6 rows. Let's maybe take one other one, for example, this one here. This is now 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It should be this one. This row here, so it's V. And think about whether you have any questions about this algorithm, because it's very important. And it's basically the zipper algorithm. So now I have table 4 from here. That's a Burgard. Burgard here, and here I have table 2, so that's 3, 4, 8, 7, 4, 6, 4, and so on. Any questions about this? Yes?
I have found a little mistake. The last one in the result is there is a Y, not a V.
Oh, yeah. I'm sorry. Thank you very much. This should be is everything else correct? Yeah, computers are much better at executing algorithms. Either they are completely wrong or it's correct. This is the merge join. Any questions?
Why do we use strings as IDs? It would be much faster to use integers.
Oh, it's a very good point, and we will see in a second whether that's true or not. It's a very good point. Is it a good idea to take the strings here? I mean, ideally, of course, the IDs are not strings, but integers. But I actually deliberately chose strings here. I mean, it works, but now I have to compare strings. I mean, zipper works with anything that can be ordered. It's a very good remark and question. And we will come to it in a second. Let's first discuss the running time. What's the running time? So for the hash join, it was size of this table, this many hash insertions into a hash map, this many lookups, writing the result. Well, what do we have here? We have 2 lists which are together as, well, you have to sort these lists. Actually, okay, what I, this, I forgot an important takes time. If the tables are already sorted, that's important by the respective, by the values in the respective column. So if they're sorted, then the zipper algorithm is actually quite efficient. It just takes time of the merged result, which is, this is also not true here. It's okay, but it's good that I realized this now, because this is not, the size of the result is also n times k, right? It depends on the, I should also have a plus n times k. Maybe where? Yeah, because the size can be larger than the sum of the two lists because I have this dot product thing going on. Okay, let me just add this here. Plus n times k. Now I have to make things blue, and now I have the where is too large here. Where? How will I do this? Where? Oh my. Where? The join, merge join takes this much time. And think about what's already on the slide. It's not too bad if there are these small mistakes, because so that's the time. So I have the two lists together, so I at least have to go through both lists. And I also, because of this cross product thing, the end result may be larger. So that's the size of the a number of rows and columns in the result. And I think that's also not quite, it's not, this here is just n when I go through this. Maybe now I can untighten this again. It's actually not so bad that we are. Let's check whether that's correct here. Please also think with me. So I have to, let's go back one slide. I have to, where's the algorithm? Here it is. I have to go through I have to iterate over the lists here, but I have to do more than, I'm touching each element more than once, maybe, right? So it's this here, for this 2-3 combination, I actually do 6 iterations over the element. First, all combinations of this with that one, this with that one. So it's size of this list plus size of this list plus number of elements here. That's, I think, accurate for the merge of these two algorithms. And then I have to write the table, which is n times k. So I think that's correct. For the merging, just touching an element in the merging, it's sum of the two lists plus n, and it's this. And this looks very similar to the hash join algorithm. It's essentially the same, with the only difference that I have, so it's basically also linear. I have size of the result table, and here I have the inputs, and the n I have here and there. But still, if the tables are sorted, this is faster, because let's just go through, I mean, you wonder maybe why. Here, a hash map is just more complicated than scanning two lists, two sorted lists, right? Inserting into a hash map is a not so trivial data structure. Just imagine this table being very large. Now I'm constructing a very big hash map, which means this constant ci here, number of insertions, that's not such a small constant. Whereas the merge join, this constant is very small. I mean, just iterating, just think about it, just iterating over these two lists, I don't have to do a lot of work, right? I just advance a pointer, I compare two values, here I have a loop-like thing. So that is, that's what's written here below. This is asymptotically the same as for the hash join, but typically this constant here is much smaller than the ci. So it's just, I don't have a complicated hash map. Okay. I think for the exercise sheet, for the new one, you should work with cost estimates, which I come to the chat in a second, which you didn't work so far in the last exercise sheet. Here are some simplistic estimates. Just take the sum of the inputs and the size of the output. And you can take these for both. Now, this is actually not an estimate. We know how large, yeah? Think about it with all the operations. That should also be clear in case that's not clear. Number of rows in the result is not clear, but number of columns is also clear. For every operation you can, I mean, let's just go back to this example. Just by looking at the input, it's hard to say how many, I'm sorry, wow. This was a new key combination, I've never seen it before. It's kind of hard to say in advance how many rows your result will have, but it's always clear how many columns it has. Yeah, it's just the sum of the two columns here. So that's always easy. So we know that. Now what about the rows? So first here I ignore the constants because I can't, we already said that, costimates just need to be good enough. Why do I take the minimum of the two? Well, that's a super simplistic assumption. I just have to make, let's go back to one result here. Just by looking at the tables, I have to say, how big is my result? How many rows is it going to have? And I just make this super simplistic assumption. If I have 4 here and 6 here, I just say, okay, everyone here will have at least one match there. It could be totally wrong, but it's not the worst assumption to make, right? Just assuming these values are all different and they all occur here. That's not a very good estimate, but as we have said in the last lecture, any estimate might be fine if it helps to differentiate different query plans enough. So for the exercise sheet, you can work with that simple estimate. You can also come up with a better one if you want. So now back to your question. Now let's play around a little bit with SQLite and let's look in the chat. So the merge join is better if the tables are similar size, and hash join is better if one of the table is a lot larger than the other because we don't have to sort. Let's look at the tables again. It's actually a complicated question. One could have people are doing hash versus merge join. There are like 10,000 papers about it, I think, and people spending half of their career on such problems. I think you are right that if one table is very small, let's maybe go to the... If one table is very small, then building this hash map is cheap. It essentially costs nothing. And then just going over the big table and looking it up in this small hash map, I think that's the most efficient way to go. Because creating the hash table costs nothing because this table is small, and lookup in a small hash table is also cheap. Now when it becomes larger, this is now the slide we are going to talk about in a second. If the tables are already sorted, you don't do a merge join. You think if the tables are not already sorted. Sometimes the tables are already sorted by the values, and that's what we will talk about next. And then a merge join is usually better unless you have the special case where one table is very small. So there is, and we'll talk about that now, there is the operation create index, very important. You usually create it for a particular column of a particular table. And it amounts to approximately sorting the table by that column. Not really sorting it, but computing a permutation that sorts it. So for example, for my movies table, I compute an index on the first column, on the ID. So I say, okay, sort it by ID or compute a permutation that sorts it by ID. Just a side remark, you could also specify a comma-separated list of columns here, but that goes too far. So that's something you can do, and we will do it in a second on the command line. And now, pay attention. When you do that, for example, I have my movies table, and in the first column, and let's maybe go right away here to just check how so this is how our movies table looked like. Here I have the ID in the first column. And let's maybe sort it on the command line. I mean, this we could do K11N. This is how you sort from the command line. Yeah. So now it would look like this, right? So now I have it sorted here according to this. Actually, what create index does, it does not sort the whole table and store a sorted copy, but it will do something like this. So in this sense, it's highly related to the merge join, right? This is one way. This is not really sorting this table according to column course, because then you would have a copy of the whole table, but just a sorted order of the values in one particular column and the row index of where it came from. This is something which Create Index could do. But actually we'll have another slide concerning what actually happens. And what this should support is, now you can iterate over the rows of the table in sorted order. So if I go here, if I would actually sort it, now I can go over them in order of sorted IDs. And another thing I can do, if I want to know in this table now, I have this sort order now, and I want to know, is there a movie with ID 27179? Then I can easily, quickly answer that question, for example, with a binary search here, right? If it's not sorted, I either need a hash map or I have to go through the whole table. If it's sorted or in some way, and we will talk about which data structures achieve this. So one way would be to just sort it, sort the values and remember the row indices. You could also sort the whole table. That's wasteful. Before we say how we do it, let's try it. This is now important, pay attention. This is a bit messy, so I don't want to write this all from scratch, it takes too long. I've just commented out stuff you can ignore, so this is, by the way, the comment where you comment out in SQL, it's just minus space. That's why it's in blue. Blue means commented out. Here I just have, and that's the data from the last exercise sheet, also from the new one, with a small variation in the new one. Please download the new data. This is our movies table, movie ID integer, title, text, and so on. We don't go through it all. So here I'm creating all the tables. Here I'm importing the data. And below I have a query. And we already had this in the last lecture. I have the query twice, once with explain query plan, so that the SQL engine, the SQLite, will tell me how it's going to execute that query, and then without it. And let's also look at the query. It's not very important what the query is. It joins 3 tables, namely it's persons, movies, and roles. So it's just the join of these, and it's just joining on the natural columns. So roles, person ID is person, persons, and movie. And it's not doing something particular. Here I select count. Why do I select count? Because I don't want to output the whole table. I just want to execute this so that it takes some time, and then I just want a one-liner. So I'm not actually interested in the result. I just want my SQL engine to have work. And what it has to do, it has to compute 2 joins here, right? That should be clear. To execute this, you have to execute 2 joins. And the order is up to the engine. So now I have, and these create index things are now commented out. And what we can do now is we can just pipe this into SQLite 3. It will always take a little because I'm always importing the data from scratch. And now we will see a number of interesting things. So this is just the result here. It's just a count. By the way, it's not important that I have the same count twice here. It's the same number, not important. It's just, the query took some time, 4 seconds. And here it says, using automatic covering index. So what's that supposed to mean? I will tell you in a second. Let's just leave it there for a second. And now let's do the following. And it's also really interesting to do this yourself. Do it, check the running time, and understand why is it faster, why is it slower, and do I understand this query plan here? Do I understand what the engine said? Now I say, okay, I'm joining these things on IDs here, movie ID, person ID. Let me create an index. So now I will compute some data structure there so that I can quickly find elements in this column, values in this column, or iterate over them in sorted order. Let's do that. Let's do the same thing. Let's see whether it helps. And I will not explain too much now, but I will just, let's just observe and then the slides explain. But this is really, really interesting. So two things you should observe. It's 4 times faster. And it's also writing something different here. Namely, it's saying, thank you for the indices, I used them here. But it's also interesting now that it says, thank you for no indices, but I used my automatic covering index. What's that? Not clear now. I will explain it in a second. Let's do another thing, and really interesting. You should do it yourself at home. Let's do, and that's why I'm importing from scratch. Don't create an index, but we have this primary key thing here, right? This is the same thing as before, but now I say movie ID and person ID are primary keys. So let's do that. And let's do the same. I'm not creating an index, but I said these are my primary key columns. Ah, interesting. Now it's even faster, and it's saying something else. Now it's also using, here it's using automatic covering index, here it's using the index I created, obviously, here it's using integer primary key, which says, I'm already saying that, when you primary key, it's also creating it knows this is the primary key. This is going to be used in all kinds of joins. That's what the primary key is for. I'm going to build an index for it, some kind of index, and it's even more efficient than this one. And let's do one more thing. Let's revert this. Let's again, not primary key, just integer. And now let's build all kinds of indices. Here I just build indices on movies and persons, but there's a third table here, roles, where I also have movie ID and person ID. Let me also build indices for those, right? When I merge persons with roles or with movies, I have a primary key here, a foreign here. It should help. Think of the merge join. And let me go back to that slide. Understand that. For this merge join to be efficient, I need this here somehow sorted and this sorted. So kind of an index here and an index here. I haven't done that so far. So now I'm creating all the indices on movies, person, roles. Let me just create an index movie ID in movies and persons and in roles. And let's do that. And let's see how fast this is. And now it's using, okay, that's interesting. Now it's persons, roles, I'm a little bit, no, I have to compare it with this one here, right? I have to check. This was the one where I had 2 indices, now I have 4 indices and it's actually slower. So it's using different indices now, but it's slower. Why is it slower if I build more indices? I mean, I can only hint at this. This is so interesting, but obviously very important in practice. Let's now go to the slides and understand everything on this page. We can understand all of it. It's actually quite easy if you know what's behind it. And then remind me, please, that we go back to this and replace this with text and see what happens, because that was your question. We can easily now say, okay, let's say this is not an integer text. Maybe it's faster, slower, same speed. Let's go to the slides and try to understand this. And play around it with yourself and try to understand it. So 2 more slides. How is create index implemented, actually? What does it do? And then how does SQLite do it? So it is not defined by the SQL standard what exactly create index does. It kind of says do something so that when join on these columns it's somehow faster. So exactly how it does this is SQLite computes an index B tree. So I don't have time and I would love to give a lecture about B tree. B tree is a kind of search tree. So if you maybe let's click on that link and see if it works. So a search tree, if you want to know about search tree, it's something like this. You have your elements here, and now you want to, this is in German, but nevertheless you will understand this is a search tree, right? You have elements, here it's just integer values, and I somehow organize them in a tree. Here it's like everything left of the tree is smaller, everything to the right is larger than this, so if I want to find an element, I'm just navigating through the tree. That's a search tree, so it's not exactly sorting the elements, but it's keeping them in some order so that I can easily find elements. And I can also easily iterate them over them in sorted order. So that's what SQLite computes, and that's fair enough. And why B tree and not search tree? I can only hint at this here. A B tree is a search tree, but importantly, I mean, if I sort my elements once, then it works for that sequence, but what if I insert or delete something in the table? That's what search trees are for, right? Now I could go and delete this 15 and I still have a tree. If I delete something from a sorted sequence, I have a problem. It's an array, I have to remove elements or so on. And a B tree is optimized for when my data is very huge and part of it resides on disk. We will not talk about this further here. I could give 3 lectures about the B tree. This we have already seen. When you say something is a primary key, SQLite 3 will automatically do this, create an index, but not for foreign keys. I think we haven't seen this. For foreign keys doesn't do this, and you wonder why, because you also want to join on foreign keys. And we have also seen this, if I have 2 indices on both of the join columns, it's even slower. Why is that? And now comes, oh, what was that? So can you draw here on the, I guess this was it me or was it somebody of you? How can I annotate? Toolgraph, got it. Yeah, we just have to live with it. I don't know where it... So, SQLite 3 does not have a hash join. That's very surprising. I mean, it's kind of the most basic operation. And if you read here, it even says, I have to go there and show this, whether fn auto, yeah, it says it here. An automatic index is about the same as a hash join. That's a very dubious statement. I mean, an index is not about the same thing as a hash join. That's for someone who has heard algorithms and data structure lecture, that's a very strange statement. But it says here. So it doesn't have a hash join, but says such thing. It doesn't have an implementation of a merge join either. So it implements neither a hash join nor a merge join. Every normal database engine has hash join and merge join. Instead, what it does, it always does the following. So if I go back to my example here, it always picks one table, goes over the elements from one table and searches them in the other table. But it doesn't search them using a hash map, but it searches them using its index data structure. So if you have an index on that one, what SQLite does, it goes over this column, and for each element here, I search it in that one, which is typically not a good algorithm. But that's what it does. And now you can also understanding that, why it's doing this here, because that's the only algorithm it has implemented. When it has to join and you haven't computed any indices, it first computes an index from scratch. That's what it's doing here, and that's why it's taking so long. It says, okay, I have to join 2 things, for example, these 2 tables, and I would need an index for this one. It's not there, so let me compute it. So it kind of does create index just for this join operation. Then it uses the index to find all these values here from this list and that list, and then it throws away the index again. So terribly inefficient. But that's, I was surprised myself. I always thought SQLite is not the fastest engine, but reasonable. I stand corrected. It's very unreasonable. It's terrible. I mean, that's a nice way to say it. It's optimized for inefficiency, I think. So more powerful, yeah, every normal engine supports, but it's very easy to use. That certainly goes for. What they write, one side remark in the documentation is they say I don't know how true this actually is, that this is supposed to work on small devices, embedded devices, so the code has to be very small, so they can't do complicated algorithms. That's actually what they, I don't know if there's, oh yeah, it was written here. That's, it's so interesting, yeah. Adding, I don't know, this sounds like I'm so sorry that this goes, yeah. That's their excuse. Adding a separate hash tables implementation would increase the size of the library for minimal performance gain. Implementing a proper algorithm would cost time and make my code larger, and who knows if it even helps. That's a very, very, very dubious statement. So we were very surprised, Sebastian and I, when we read this, to find these very dubious statements here. Of course, they are deep. 14.1 somewhere on a subpage about optimization. Let's do one final thing here, and let's do text here and see what happens. Text. What do you think? Same speed, faster? It's very hard to predict for SQLite 3 because it does these. And we just have movies, persons, and so let's just pick text here. And there's of course more to understand, but I will not talk about it here. Let's remove the indices here. So now now my keys are text, and let's just execute it. It will import the files. Actually, I'm not sure. Okay, it computes an automatic covering index. I don't have an index, so I compute one. Okay, so you see, it's slower, as one would expect, but also not super slow, but that's only because the other stuff is already so inefficient that it... You also see the performance differences are not huge, right? Factor 2, 3, but that's because it's like in Python, everything is inefficient already in principle, and then algorithms don't make such a big difference. In C++, you would see performance difference of a factor of 10 or so, if you do strings or integers. Okay, that was, I think, any questions about this before we, I think, make a short break and move on to the other stuff? Yes, please?
Go back to slide 9.
Yes?
You briefly added the k and then removed it, because you said we look at n multiple times. But we don't we also look at k multiple times if you take the mini cross product on the left and on the right?
So you are advocating for having n times k here?
N plus k. You added the k, but...
Okay, let me just clarify what the k is. The k is the number of columns. And I think for doing what I'm doing here, the number of columns plays no role. The number of... So maybe it's a confusion about what the k is. The k is just when I write the results, I'm actually writing all the columns. Here I'm dealing with abstract representations. So for all this, it doesn't matter whether this table has 500 columns or 2. Good question. Any other question for now? Okay, so let's have a break and then resume in 5 minutes. Thank you. Okay. So maybe you're a little bit scared that we only have 1/3 of the slides so far, but it's half time already. But it shouldn't be a problem because this was very interesting and also a bit more deeper. The rest, I think, is easier and lots of examples. So I think we will be fine. But nevertheless important. So first, more join operations. And I think much of the following will be easy to understand, but please pay attention. So far, so we have join. The join, there's a reason why we talk so much about joins, because it's a central operation in databases, different tables, combining them. And what we typically did so far, let me just show it again. You have values here, and in the result you only have rows for those values which occur here and there. And the question is, what about this one? It's here but not there. Should we include it or not? And there are variations of the join which include it, and we will talk about them now. So, what we did so far is an inner join, and it boils down to list intersection. Just consider those values which occur in both tables. We could also say, and this T2 is not blue, so we cannot continue. Oh wow, why is this not? Yeah, we can't continue before we make this blue. I'm sorry. Roadblock. Let's just say if a value does not occurs on the left in the first table and not on the right, let's include it anyway. That's called a left outer join. And similarly, the other way, it's a right outer join. And this should be, let me also fix this right away because it's quick. That should be here a subscript. And you can also include them from both sides. That would be called an outer join or a full outer join. Here's an example. So that's the same table as before. Without the yellow thing, it's the same table as before. But now I say, okay, here's a value in the join column. So I'm joining on the course column, which is only in the left table and not in the right table. Then I'm including it anyway. But now what do I include here? I don't have a row in the second table, so I just put null. And we haven't talked about null here, and I don't have, null is a special value. I think that's good enough for now. Is a special value where you just know it's null. I mean, any programming language, any system has a special value for null. So I think that's simple enough. You have to know the syntax, and it's called left join. And I will come back to this thing here in a second. Left join, so instead of comma, I write left join. Instead of where, I write on. So now I'm including also rows where this here is not occurring here. And let me just show you an example for the right outer join. So now here I have, and maybe let's also highlight that here. So this is about this one here, right, which doesn't have a counterpart on the right. And here I should have two students, namely these here, which don't have the course does not exist on the left, and I want to include them anyway in the result, and this can be useful sometimes. And so I just include these results. And if I do a full outer join or just outer join, you could, I think, also write right outer join here. Then I would have this row and this row. Yes?
In the students table, there is a student with the course number B2060. Shouldn't that be?
Oh my! Yes, it's the same mistake like before, right? Yeah, it's my, I somehow also in the preparation, I overlooked this poor student. You're absolutely right. And I will solve this as follows. Thank you. I think I will just, oh no, this is not what thank you. Let's let's solve this right away, and because actually I added a row here just so that you see there's not always just one row which is added here. So let's do this one. This is this one, and here we should get this 260 students. And let's check whether it's correct. Is this correct now? 7, 3, 4, 5, 3, 4. Do you agree? Does it look correct? It's now this one which doesn't have a counterpart and table on the left, and this one. Yeah? Okay, thank you very much for paying attention. Yes, absolutely right. So it can be any number of rows here, which, okay, let's continue. And if you just want both, then, and so, yeah, we'll see in a second that SQL is a huge language. There are many. Then there is the natural join, and I just wanted to mention it. It's not actually something new, but typically, I mean, so far we always wrote tables, comma, tables, where, and then say this column is equal to this column. You can also write join on. I will come back to this in a second. If the columns are the same, you can just write natural join, and it just will join it on all the columns which have the same name in both tables, which is frequently the case, right? You have something movies ID, then in every table which has that ID, you call it movies ID, whether it's primary or foreign key. So these three, so that's what I was talking about. Now I have my tables, profs and studis from before. Everything is text for simplicity. So let's join them on the course column here, which is the same in both. So that's the old-fashioned way to write it. Profs, comma, studis, so like Cartesian product, but then only take those where the two are equal. You can equivalently write it like this. This is all three give exactly the same result. Join on, that's now an inner join, so no extra rows if it only occurs on one side. Or you say natural join, and natural join is just an equi-join on the columns where the name of the column is equal, which is here just one column. The question, so that's one thing about SQL which one cannot like with some justice, I think, that you have so many different ways to write the same thing. So which one should you take? This is, I think, from ancient times. This is like very basic SQL. This is how we started. You can write all select queries like select from where. And you can even only do it with Cartesian product and project and select. This here is the more modern way where you make explicit that this is a join operation. Here the join operation is kind of implicit. I mean, let me just say that again. When you give this to a database engine, it will do a join even though you didn't write join here. Here you make it explicit, and here it's implicit on which columns you are joining. So kind of, you won't see that so often, but it's very easy to write. Okay, that's the natural join. And just to show it to you that this exists, so far our join conditions were always this is equal to this. Let me give you one natural example that this doesn't have to be so. So here, let's assume I have bus stops. So they have a name and some geolocation. And I have restaurants. They have a name and some geolocations. And now I want to join them, all bus stops and all restaurants, but I only want those pairs where the bus stop and the restaurant are nearby. So within 500 meters, less than 500 meters of each other. Now this syntax requires some special extension, but I think you get the idea. So now I have a join. Consider all combinations where the two are close together. This is called a spatial join. Maybe I should write this here. And that's not the topic. So this is called, and it's a very spatial databases where things have geo information, and then you could do all kinds of fancy stuff. You could give a whole course about this, and we are also doing this a lot. So this is called spatial join. But it's an example. And of course, you have the same efficiency problems here. If you have 1 million bus stops all over the world and 1 million restaurants, you don't want to compute the Cartesian product here, right? And then filter. That takes way too long. You need a data structure. Actually, the data structure here would be an R tree, some geometric tree. some division of the plane. So you have similar efficiency issues. There's a question?
Is it possible to join on that it only shows rows where one thing from one table is smaller than the thing from the second table? Is it possible?
So just instead of equal, less than? Absolutely. Yes, you can do that. And for every join you can always compute it like Cartesian product first and then just filter. That's the inefficient way. And then there's always the question to ask, let's say it's less or equal, can I profit from an indexed data structure? And for less or equal you also can, right? You can somehow, if you have a search tree over one column, you can make it more efficient. But yeah, you can do that. You can write anything, the question is just how efficient it is. And here there are special data structures for making that efficient. And actually, let me just, I think we have this, let me just quickly check. I think we have this query here, right? On our, do we have, I'm blind. Oh, maybe we only have it for Germany instance. Let me see. Restaurants in Freiburg near tram stop. Let's see whether this works. Oh yeah, it works. Okay, here we have all restaurants in Freiburg. That's a query on a. So here we have it. Yeah, it's exactly such a query. So now you have, Spice Trails is near Bertholdsbrunn and so on. So you just saw it in action. Okay, but that's just one example of a non-equi join. Now I have a whole section about grouping, because group by, and this will also be on the exercise sheet, that's the one really basic operation which is non-trivial, which we didn't talk about so far. And we will just see it by an example. I will not talk too much about let's say we have our movies file and we want all movies from the same director and take their average score. And this is also what you have on the exercise sheet. So they are all movies by Steven Spielberg, all movies by Christopher Nolan. So I want to group the movies, in this case by director, and then for each group compute something interesting. For example, the average movie score of a movie from that director. This you do with group by. And I'm not sure, I will do this for the last time in this lecture. Actually, Sebastian, do we need this operation for the? Yeah, you have to implement it. You don't have to. You don't really need the formal definition. I've added the formal definition here, and you can see it's super complicated, but it's actually not so hard. I will not talk about this slide. It costs way too much time to make it, because writing down more complex SQL operations in their full detail is quite cumbersome. It's easier to implement than to write down the definition, but I just want to mention that this P of X is supposed to be the set of all multi-sets X prime of, it's the power set. It's just all subsets, but with multi. And this was written too hastily, so I should just write it again, because I was thinking and writing at the same time. And this is a calligraphic P. Let me just write that again. I mean, you can look at the slide where it's there. P of X, that's the set of all subsets. It's the of all multi-sets X prime, which are subset of X. I think I could spend half an hour explaining this definition. This is actually a good example where I'm not sure mathematics is so helpful. You have to implement this for the exercise sheet, but the implementation is way easier than the formal definition. So it's probably easiest to to explain this in terms of the implementation. And I will just explain it by an example, because that's very easy to understand. Group by is really easy to understand, but it has a lot of border cases, and maybe we'll talk about some of them. So here I have my movies table in the simplest of form, no IDs. Name, title, actually, yeah, name, it says here name, maybe it should be title. I think it would be a bit better to call it title, because we called it title before, so it's the title of the movie. Let me also call it title here. PowerPoint will. Yeah, and I've abbreviated the movies here a little bit, so this is all quiet on the Western Front, but actually I deliberately chose short movie titles, this movie in this year. Now this is my query. Select something, we will look at this in a second, from this one table, no joins involved, group by year. So I'm grouping by year, which means in my result I will have one row per year now. So here I have just 3 different years, right? It's 23, 22, 21. By the way, they don't have to be together in the table here. And now, for each group I do something, and what do? I now have to say this here. So for the things which I group by, I can just write them here. So I have one group by year, so I just have year here. And for the things which I don't group by, I have to say, what do I do with them, right? Understand this thing. It's easy enough to understand. For example, let me just highlight this here. Here I have 3 movies from the year 2022, and here I have one entry in my result table. So understand why I don't have to write anything specific for year, because I'm grouping by year, which means all these things in the same group have the same year. So it's clear what to put here. It's just the common year of this group. But now I have to say, which score should I put here? The result is always a table. So here's one thing. I should say max. Just take the maximum of these. So it's like an aggregation function which takes a number of values, a set of values from this domain, and gives me a value from another domain. Here it's the same domain, could also be a different domain. So, and here all kinds of function available. I could sum them up, I could compute the average, I could concatenate them. Yes, please?
Shouldn't the header of the resulting table be max score?
Yeah, absolutely right. It should be max score, yes. And this is, actually I'm not sure in SQL whether you could write it. I'm not sure whether you're allowed to call it the same name. Maybe you can look it up, someone can look it up. Max score. So now I have to, yeah, it should absolutely be max score. Thank you. Let me just write these. So I'm really bad at drawing rectangular things, but it's very hard with this pen. Okay, that's group by. And I think it's simple enough. And maybe let's go back to the definition now and try to understand it a little bit. I think it's clear to understand what's going in here. The input is a table. This is the column indices by which I group by. It's the second column. This could be, you could have any sequence of column indices here. You could even have year twice if you want. Doesn't make sense, but you could have. And here you say, for the other columns, so for example for column 3, I want to also have it in my result, and then you have to say, how do I aggregate all the things in the same group with max? Maybe let's go back to the previous slide, we can understand it a little bit. So that's what it says here. So it has 2 arguments. These are the columns by which I group. These are column indices, and these are the aggregation columns. So I also have column indices. For each I have an aggregation function. Think about this, why that's correct. It's important. This thing is important, and you can understand it. Either a column is in the group by, it defines what a group is, or it's a column for which I have to aggregate. If it's not something by which I group, I might have several of them. I have to say, how do I turn several of them into one? And M, I must have one column by which I group, otherwise the group by doesn't make sense, right? So this M must be greater or equal to 1. I can't say group by nothing. But these can be empty. I don't have to, actually this is a special case. If I don't have the max score here and just a year, then this is equivalent to distinct year, right? Then I just have the distinct years here. So group by something without aggregation function is the same as distinct. And another example that you have can write the exactly same thing in many different ways. So in that case, it would be good to just do a distinct. That's the group by, and you have to implement it. It's actually, I think I have some implementation advice. Here's one more detail. There's another keyword having, and if you've never seen this, you wonder, why do I need another keyword having? Assume I want to show only groups where this max score fulfills a certain property, like only show me the years where the max score is greater than 8.0. So this would go away. Well, how do I write this in this query? I can't really write it with, the where clause would go before the group by clause. The thing is that the max score only exists after the group by, right? It doesn't exist before. I mean, I could write here where year is after the year 2000. This I could do. I could just write a year here, but I could not write where max score is greater than 80 because the max score is only defined by the group by. And that's why I have a having. Here's a having clause. Yeah, and this is how I could include it in the definition. So now I'm saying my group by creates new variables, max score in this case, and I have to make the same correction here, and I will do it. Max score. Yeah. So this is created by the group by. I have a max score, and now I have to say, and this is also wrong, this should be max score now. And this is now, so this is having. If I have a constraint on something that is only created by the group by, I cannot write it in my where clause, which would go here. I have to write it in a having clause, which comes after the group by. That's why you have having. I think it's easy enough to understand. At some point you will need it, and then you will see. How do I implement it? Well, the natural implementation is, and you should implement it for the exercise sheet, just think about a single column with values, then it's easiest. I go over this, I just do a hash map where the keys are the years, and then I just put all the values in the, so let's just do how would the hash map look like here? It would look like this, 2023. And then I just collect the values while I'm going over this. Then I have 2022, I go over the table, and while I go over it, I collect the values 8.6, 7.8, 7.7, and then I have 2021, and by the way, they don't have to be in order for that to work, and they typically are not, right? 8.0, 7.5, so that's how you would implement this. You would compute this hash map, and now you make a pass over the hash map, and for each set of values here, you just apply your aggregation function, which means you would just apply max here. So if you do max here, you get 8.5, you do max here, you get 8.6, you do max here, you get 8.0. So it's not hard to. Sebastian, do we need cost estimates for the group by operation for the exercise sheet? We don't need them. I've written them on the slides anyway, just in case. Now, we have a similar problem. If we need cost estimates, how do we know what the result is? It's very hard to know. It depends on how large the groups are, how many How often will I have each year here? So I can just make some educated guesses. And it's not important, I've just written it on the slides. Here's some random assumption. How hard is it to evaluate the aggregation function? This max here, max is easy, could also be something very complicated. So the cost of this operation depends on the details of the table, details of the function, and so on. And here's, that's interesting, and I think you also need it for the exercise sheet. Pay attention, because that's interesting. Think about the following. Let's go back to this table. Here, I have grouped by year, and I've output the max score for year. Or maybe let's go to the table without the having, because the having is not important here. Now assume for each year I want the movie which has this maximum score. Think about it, how would you express it in SQL? So it's very simple query for each year, the highest score. That's what I've done here, group by year, and then max score is max score. And now I want the movie with that score. So here I would want Kashmir Files, here I would want Oppenheimer, here I would want Dune. And if you think about it, you can't do this with the normal group by. What you could do is, you could now write, somehow what group by allows you is, which of these three, Kashmir Files, Western Front, The Whale, how do I select? I could say, give me the maximum of those, the lexicographically smallest or largest. What group by does not allow to express, give me the movie for these three, how do I select one? Give me the one where a value in the other column is maximal. Group by does not allow you to express that. That's what I want for example, in my example here. Have a column title here where you should write the movie with a property that doesn't only depend on that column, but the movie which achieves the maximum score, maximum value in the score column. It's not easy, but it can be done, but with a detour. And that's a nice task for the exercise sheet. You have to think about how you do it. Because that's, and it's interesting, that occurs very frequently and you can't do it easily. There is no, how do we get the, and that's what on that slide. And you have to figure it out yourself, how to do it. It's, which exercise is it? Exercise 2 or 3? Where you have to do that kind of query? It's 3, it's the third exercise. Okay, maybe we go to the exercise sheet now to just look at to motivate you. So the exercise sheet is now more advanced stuff, and it's like practicing all the things we have seen. So here you have, and now we don't, interesting queries on the, and by the way, we have new data with a little bit more information, which we needed to make more interesting queries. Here we have all movies that won an Oscar in any category. The reason for the year restriction is just so that the result is not so big. And here you should play around with cost estimates. We have already talked about them in the last lecture, but you haven't really played with them in the exercise sheet. This is about implementing group by and then trying it out for a query. And this is, And this is the kind of query which we have just seen. You want the query, you want the highest IMDb score for each decade, again decade, so that you don't have such a big result. So the best movie of the decade, and then which movie it is. And you have to think about how can you do this with SQL, given the problem I just said. So there are some questions in the chat. we cannot give one distinct title to the score because there could be multiple movies with the same score. Yeah, that's true. That's another complication. If you have multiple with the highest score, then you have to say what you want. Do I want all of them or just one of them? You could say, give me just one of them. Or more of them, then you would have multiple rows. Okay, good questions. So here's some more SQL. Okay. This was just super basic SQL. There are many, 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 many more. Here's the SQL standard. Let's look at the SQL standard. It's exciting. Let's look at it. Here's the standard. And let's look at part 1. That's also interesting because it's expensive. That's just part 1 of the SQL standards. I think it's 100 pages or so, and it costs 189. Only if you are a full member. Otherwise, it's so it's interesting that the standard is not free. It's actually typical. We discussed about this yesterday, and this. So 1, 2, 3, 4. Yeah. So the actually was 5, 6, 7, 8. I don't know. So the SQL standard is a huge. SQL is a monster, right? By the way, the C++ standard, it's similar. If you want to read the whole standard, it's a huge document and it's not free because standard committees are a lot of work and cost money. So in this course, we just provide the most basic operations, which are enough for many SQL queries. I already showed you this page here. If you click on select here, we will see other queries in a second. Here you see always a nice diagram which shows you how you can create the select queries. We've already seen some things: distinct, from, where, group by, having. So some things should look familiar, but there are also actually not too many other things. We will see order by, limit and offset in a second. We will not talk about values. We will not talk about width. So it's not, yeah, it's, but, so these I will now explain by example, but just by example. No more formal operations, and they are very easy to understand. Especially the first two, subqueries, I have 2 slides. Subqueries are very important. And you need all of them for the exercise sheet. Order by. Order by is easy. I mean, so far, things are always multi-sets, which means the order of the row does not matter. But in the end result, the order of the rows often does matter. So, yeah, you can just do it like this. And I think I don't give an example because it's, maybe I don't know. Should I give an example? Why not? Let's give an example. So we have, how do I, let's see, if I select star from movies, let's just see whether that works. Let's pipe it into our SQLite 3, and I think I've already created the database file where everything is in there. Let's just see whether it works. Movies, DB. And let's do no such file or directory. Oh, echo. Okay, I have to. No such table. Okay, maybe I should. Let's see. Do I have my tables in here? No. Oh, my movies DB is empty. Ah, because I haven't copied it. I'm sorry. I forgot to copy it. I think I have it here. Internal code lecture 4 movies DB. That's why it didn't work. Yeah. Okay, that takes a while. That's good. That has a certain size. Otherwise, I would have to import everything. What? Can't be that large. How big is it? 371 megabyte. That took a bit too long. Okay, yeah, that works. Okay, let's just make this a little bit larger because I don't need the other window, and let's just, yeah, okay. Let's maybe just select title, comma, year from movies. Okay. Now I just head here, I just want the first 10 lines. Okay, so I'm just doing it here on the fly. I just pipe this string into this and see it. So now we can just do order by year. So now I get them in any order. It's probably the order in which they were in the input files. And now you see no particular order, neither first column nor second column. Now let's order by year. Now I get them ordered by year. And because I did head, I just get the first 10. 1875, you see it's ordered by year. How do I order in the opposite direction? Well, there is ascending and descending. If you don't say anything at ascending, I could also write it here. ASC is the same thing if I write DESC. And note that this comes at the end. So order by year, the order by comes after everything else. Now it's descending. Okay, now I get some with empty year. I wasn't aware that we had those. The empty year is apparently the largest here. Okay, that's order by. Then there's also limit. Here I did it like this, that I just, if I don't restrict it, let's go back to ask again. I get the full result of everything. Maybe I want it to be part of the Sparkle query to just give me the first 10 rows, and you can just write it like at the very end, limit. So, title year of all movies, order by year, ascending, always good to write it explicitly, just give me the first 10. There we are. Or just give me the first 20. These are the first 20. Or maybe I want a segment in between. I could also do that. Give me 2 starting from offset 10. And this should be now, this should be number 10 and 11 here, right? So this, if you just want a segment from the sorted result. I can also do it without order by, but that doesn't make a lot of sense because I don't know which segment I'm getting. So that's a typical combination. Order my table somehow and then give me a segment of the result. Typically don't have offset you use when you have big data and you want to read it in chunks, but simple enough to understand. And you could also have several keys here separated by comma, then it's like first order by year, and for the same year, if you want to break ties, then use this column, and so on. So that's written here on the slide. Any question about order by and limit and offset? I think it's simple enough to... Can you exclude empty year with this line? Yes, we can. It's the same question, and maybe we should try it together. How do I exclude empty years? Who has an idea? I want to exclude, I think probably I want something not null, right? Where? Who knows how to do this? Where year is not null? I don't know. Sometimes in SQL you can just write it. Yeah, that I could write it, but it didn't do what I intended. Maybe it's just the empty string and not null. Yeah, that was it. It was just the empty string. Okay. And here, that was interesting because here again you see the order. Order is important. Select from. Then you have all your where constraints. And then in the very end you say, okay, now my result, order it like this, and just do a subset of it. So, important but easy, right? Now I have just the top 10 movies when I order them by an actual year, which is not the empty string. What else? Okay, subqueries is important, but also not really new. Think about it, everything we did so far, and maybe let me quickly go back to lecture where we had this. So anything the database does is really it gets tables and has operations which again produce tables. Everything is tables, all the way from bottom to top. Tables all the way down. Tables, product, table, table. All operations take a table, produce a table. So, a select query also gives you a table. So far we had one select query and it gives you a table in the end. Because it also gives you a table, you can also have a select query inside a select query, or many of them. And here's an example. And now, I mean, this is typical for computer science. You have relatively simple concepts, but when you plug them together, you get complicated things. Let's look at that query and try to understand it. So now I have, let's first understand it on a syntactic level. I have select from table, join with another table on join column. We have seen that syntax before. Join on another table on join column. But now, instead of another table, I just write a whole select query, which gives me a table. So I can just do that. All I have to do is write parentheses around it. Wherever in a SQL query I can have a table, usually I put a table name. I now put a whole subquery and have to give it a name with as. By the way, as, we haven't seen that. You can also use that for other tables. I could write movies as M, and then I could use M instead of movies or something like this. So I think understanding when you can do it is easy. Wherever you can write a table, you can also write a whole select query, which gives you a table. The question is what it means. Maybe think about it a little bit and then let's look at what it means, this query. And I tell you how to. Or does anybody see immediately what this query computes? Yes?
All movies where the director was awarded an Academy Award?
All movies where the director won an Academy Award. Yes, that's exactly right. Very good. Okay, let's see how one could get at that. Actually, these quickly become frightening because they can become big. And you need this for exercise 3. And hint for those listening here, I had this, and this is often the answer. We said here, if you want this, you want the movie, the highest score per year or per decade, and the movie belonging to it. You can't do this with group by alone. You can do it with group by and subqueries. And very frequently, when you can't do something immediately, you can somehow do it with subqueries. So, hint, that's also the solution here. How do we understand the query? Well, let's just look. Let's just assume the result of this subquery were an input table. And let's look what this query does. That's the subquery itself is easy enough to understand, right? It's just I have this awards table, and I just look at the persons who have won an Academy Award, and each person at most once. So let's just replace this with a table like if it was one of our input tables. And then we have this situation. We have our typical movies table, the director, who directed which movie, and who won an Oscar. I could have called this Oscar winners, but then it would have been too long. And now my query becomes the following. It's just, look at the query, it's just joining 3 tables, movies, directors, and the Oscar winners. And it's even joining them in the natural way, namely here on movie ID and on person ID. So using what I wrote earlier, this is a natural join. So I'm just joining these 3 tables together in the obvious way, namely on the join column, movie ID, person ID. Well, what happens if I movies, directors, Oscar winners? Then it's easier to see that this is all movies with a director who is an Oscar winner. That's easier to see. So if you want to understand a query with subqueries, think about what's the table produced by the subquery. Think about it as if it were an input table, and you can do that recursively. If you have many of those, then it's usually easy to understand. Okay. And you need that for exercise 3 and for this special group by thing. So now we go acid, last part. This is quick. Is there any question about this before we go to this last part, which I think will not take long, just 5 minutes? Okay, let's go onto an acid trip. So dynamically changing tables. So far, we always did the following, and it's actually a frequent use case. We read our tables and then we asked queries on it, right? And let me just say it again, that's a very frequent use case. For example, Wikidata, which we have seen now several times, many data sets out there, they get updated once per week, maybe once per day if they're smaller, some even once every 3 months because they're so big. So it's perfectly reasonable. There's a new version. I load this new version into my database, maybe it takes a day, and then I work with it for 3 months until the next version comes around. So nothing changes. I read the data once and then I query it. But of course there are other applications where that is not so. Typical example is bank data. Yeah, banks have all who has how much money on their accounts. This changes all the time. People are transferring money. And of course this is stored in kind of database. Product data, you're a company, you have lots of products, the products change, you buy new products, you sell products, the price changes, the description changes. And of course HIS-IN-1 is, it's a database, and you have people have these grades, people joining, people leaving. I mean, that's also very, very normal. HIS-IN-1 just consists of hundreds of tables, and the contents changes all the time, constantly. And so just 2 slides. How do you change rows? There's of course also SQL commands for that, and it's very easy, the basic commands. Let's just start with our very simple movie from the beginning, and this is very easy. I just wanted to show it to you. There are 3 things you can do with the table. Add a new row, insert into table, and then you just specify the values of the new row. Maybe you want to change a row. Okay, I want to change the row where the title is Inception. Usually you would do this via the primary key, but maybe let's do it like this here. Maybe I want to update the score. You do it like this. Or maybe I want to delete the row, or many rows. Delete all rows where the year, all movies before 2000. So changing the rows, these are the 3 main commands. Insert, change, delete. So we had this at the very beginning, change in the columns. Don't do it, but you can do it. Again, here I don't have a table to go with it, just you can add a column. When you add a column, you have to say, what should I put in the column? It will be all null values, I think, is the default. You can remove a column. Everything that's in that column will then be gone. And you can rename a column. And you can change the domain name of a column. So maybe I've changed score to rating, and it should be no longer real, but int. You can also do that. Wait. Careful just has 1 L, right? What? No, I'm here on the careful. I think that comes from carefully, from my correction. Now it looks like it's perfectly reasonable to, and just understand this. I mean, changing the rows in a table is perfectly normal. It's not symmetric. I want you to understand this, right? Changing the content, HIS-IN-1, changing the content, new grades or something, that's perfectly normal. Changing the columns is not perfectly normal, right? Think about HIS-IN-1, there's all kinds of services, things doing something with a table, they are relying on a structure of a table. If you now, let me rename that table to something else, let me remove that column, then 1,000 things, 1,000 people using your table services, they won't work anymore. So this is something, don't do it. Maybe there are there are cases where one wants to do it, but then it usually has a whole tail of things which follow. So this is not symmetric. The columns of a table, think of them more as fixed. And this is something I only want to mention because it's important. We don't go any deeper here. Transactions. But I did want to mention it. These are the last 2 slides of the lecture. When you change the contents, you have to, you change the grade, you transfer money. You have to be very careful what happens when something goes wrong, right? And if you just, in our setting so far, where you just read it once and then you ask queries, all that happens is the query fails, you have to ask it again, But if you transfer money and something goes wrong, you have to pay attention to things like the money being subtracted from my account, but not being added to the other account. The bank just said, oh, sorry, that happens. Something went wrong. It wasn't our fault. It just shouldn't happen, right? Subtracted here, not added here. That's very frequent. And so that's why in real databases, in these situations where the data is not read-only, you have the concept of a transaction. So things which somehow belong together, money being subtracted here and added here, should be considered as one unit. And that's where ACID comes from. And you could give again a whole course or many lectures about ACID. But I just wanted to mention them. And you should at least understand them. So atomicity is, think of the money transfer thing, either this works or it doesn't, nothing in between. Either the money successfully is subtracted here and added here, or nothing happened. There shouldn't be an in-between thing, because something... And you have to implement this. What happens? You're doing this, your code runs, and then something crashes. You somehow have to take care of this. Then there is consistency, isolation, and maybe I will spend 1 more minute to explain them. And durability, that's again easy to explain. The transfer succeeded. You go to your web app, your banking app. The money was transferred. It says transfer successful, and at that moment the bank computer crashes or something. After it told you that it actually worked, then somehow they have to make sure that it still doesn't get lost, because there are actual systems behind them, data being stored somewhere, and so on. So actually the Wikipedia article has very nice examples for all 4 of them, for atomicity, and I couldn't explain it any better here. And I'm not sure, and they give 4 examples for each of them. So you maybe wonder what you should remember from this. For the exam, you should know that ACID exists. These 4, it's just, you should just know them, and you should understand what the difference between the 4 is. So I would say go to the Wikipedia page and read the examples. And maybe before we close, I think I should... I don't know. Maybe I do it at the beginning of the next lecture, because we're already over time now. Maybe I will come back to this now. I don't want to start this from scratch. But anyway, we're not going any deeper here, but I did want to mention it because it's very important in many applications. Any questions about the material today or about the exercise sheet? Okay. No questions, so have fun with the sheet and see you again next week. Bye-bye.